Hey, let's look at the average power. For the AC signals, most of the time, we are more interested in the average power rather than the instantaneous power. Let's look at the average power, how this is defined. So let's use the capital T to denote the average power, and that capital P is related to the instantaneous power by this integration. If we integrate the instantaneous power over time, and what do we get? This is the energy, right? So we divided this total energy by the time interval we integrate. This is T is the period. T is the period of the instantaneous power. Remember the instantaneous power, let's see, they have the AC term, right? So this AC term, they will have a frequency. That frequency will have a period. So that's the period of the instantaneous power. So let's look at the piece for the resistance. For the resistance, we just did a moment ago, and we have the instantaneous power for resistance just a half I sub A square times R plus half I sub A square times R times cosine 2 omega t. So in this case, the period for this term at the average, you could use the t. You can choose t is equal to pi over omega. Right? So that's the one way to choose the t. Or you can choose the t equal to pi over 2 omega. Because the omega is the frequency of the current and voltage, and the power actually, the instantaneous power actually varies in two cycles. Had two peaks in this period, right? So therefore, either way, when you integrate these, I don't really need to go actual integration, because I know either you integrate, let's see, if you have a cosine signal, either you integrate in one cycle or two cycles, right? The area underneath is always gonna add up to 0, although my drawing is not perfect. So therefore the second term, if you integrate that, the integration will give you 0. The first term, this is a constant. Therefore for P, let's say capital P sub R, it's just equal 1 over T, 0 to T, P sub RT. That's just equal to half IA squared times R, because we can dt. And so in this case, because this term is a constant, I can move that out. So therefore you have the integration becomes t, and divided by t, that's 1. So therefore you have this term. The second term integration, the AC term, going to disappear because of these. Right? So I don't have to go through the math. For the inductance, the instantaneous power P sub L t is equal to negative half omega L I sub A square if the current, this is the amplitude of the current source, times sine 2 omega t. And if I integrate this over a fundamental period, I get a P, the average power P is going to be equal to 0, right? Because this is pure sinusoidal, I can do the similar thing for the capacitance. The capacitance we have is a half omega c times V sub A square times sine 2 omega t. And again here, because this is the only pure AC, there's no offset or DC components, and then we have P sub C, the average power absorbed by the capacitance is 0. Always the case. So for example, if we have a current source, right? We have a current source flowing through a inductor and also flowing a resistance here. And the inductor here is the inductance L, here is this R. So let's see this IT, give a number here, let's see, this is the 10 amps times this cosine 100t. That's 100 is basically angular frequency omega. right? So in this case, the power absorbed or supplied by, drawn from the source or supplied by the current source is, in this case, the power is going to be, let's see, use that as a P, and the P is just equal to the I sub A half I sub A square, which is 10 square times R. So whatever the R is, so the resistance value, whatever it is, so that would be 50 times R. The unit typically would be watts. So that's how, in this case, I don't really need to care about the inductance, because the inductance will not give you any, will not absorb any average power. Let's look at another example. Let's see if I have the voltage source. Let's see, I have, in this case, let's see the Vs. This is given in the phasor. Let's see, this equal 20 volts. The phase angle is not really critical. And in this case, I have a capacitance. Let's see, this is equal negative 5J. And some of you asked why the impedance for capacitance is always a kind of negative part, have a negative sign, because 1 over j omega c, I think I mentioned one time, 1 over j omega c, omega is a positive number, and c capacitance is a positive number. 1 over j is equal negative j, right? So that's equal negative j times omega c. That's where this coming from, where this negative sign comes from. Let's see, I have a resistance here. Let's see, I have a 2 ohm resistance. And in this case, let's see, find the power supplied by the source, the power supplied by the voltage source, or I'm talking about the average. In this case, I'm also talking about the average. So the average power supplied by the source, or we can also see the average power, which is equivalent to see the average power, the power absorbed by the RC load. Okay. And in this case, we know the capacitor will not absorb average power. Therefore, we only care about the average power absorbed by the resistance. And in this case, we still use let's see, the P is going to be equal half IA, and the IA is going to be equal to voltage magnitude, right? That's 20 divided by the resistance. So that will give me the amplitude of the current, that's square, times the resistance R, which is 2. So in this case, I will have 10. So I get 100 watts. So this circuit, actually the source is delivering 100 watts to the RC load, where the average 100 watts is absorbed by the resistance only, because the capacitor will not absorb the average power. I hope that will explain the average power concept, which is very important. Okay, so the next one would be the maximum power. How we can draw the maximum power if we have the Thevenin equivalent circuit already kind of modeled. See you in a moment.